Professor Tera again for inviting me and the opportunity of this talk. So in this talk, I will talk about the story in the case of 10 harmonic bundles, and the base space is one-dimensional. So in that case, everything is simpler. So, and then I will explain something more about wild harmonic bundles. But anyway, so let me remind you the definition of harmonic bundles first. So let X complex manifold. In this case, this is n dimension, arbitrary dimension, and we consider holomorphic vector bundle. And this theta denotes the Higgs field, which is holomorphic section of omega x1 such that theta square equals 0. And so if we are given Hermitian metric of the bundle, we have the Chern connection, which is a unitary connection determined by the holomorphic structure and the metric H. That is a unique unitary connection whose 0,1 part is equal to the given holomorphic structure. And we also have the adjoint of theta. With respect to the metric H. Then, if the metric is called pure harmonic, if the connection obtained as the sum of the Chern connection and the Higgs field and its adjoint is integrable. And in this case, the tuple of Higgs bundle with pure harmonic metric is called harmonic bundle. So, the condition is, so this is the integral. So this means the curvature is 0, so which means del E theta equals 0. And del E bar theta ga equals 0. And Hitch equation. So this is the condition. Okay, and then let me show you some easy examples. For instance, if equal just is structure shift and theta equals derivative of some holomorphic function, and metric is given by the easiest one. I mean, one is the section of this sheaf, and the norm of 1 with respect to metric is 1. This is the simplest one. Then it is easy to check. Theta H is harmonic bundle. And slightly more generally, so in the rank 1 case, harmonic bundle is easy. So harmonic bundle of rank 1 which is just a pair of triple holomorphic one form, holomorphic vector bundle, line bundle. And closed one form. And metric H, for which the charm connection is flat, integral. So maybe it's better to say this is lemma. So I mean, so in the rank 1 case, this part is always 0. The commutator of the Higgs field and its adjoint is always 0. So this condition is just the curvature of charm connection is 0. And in the rank 1 case, theta is just a holomorphic one form. So so theta is holomorphic, assumed to be holomorphic. So this means theta is a closed form. So so it is easy to see harmonic bundle of rank 1 is just triple of holomorphic line bundle and closed holomorphic one form, and the metric whose charm connection is integral. So the point is the conditions are separated. So in the rank 1 case, harmonic bundle is much easier to compared with the higher rank case. And another important example is given by polarized variation of Cauchy structures. Which is maybe it's better to say complex polarized complex variation Cauchy structure. Which means so we are given some vector bundle with grading, and flat connection, integrable connection, such that nabla, the image of VPQ is contained in VP plus 1, Q minus 1, tensor omega 01 plus VPQ tensor omega 01 plus omega 10 plus V P minus 1 Q plus 1 tensor omega 10. This condition is so-called Griffith's transversality. And so this vector bundle connection, flat connections, and polarization, which is flat pairing Hermitian pairing. Sorry, not Hermitian. which is a minus W Hermitian pairing. Hermitian. Sorry, so, and this is flat. And VPQ, the decomposition of VPQ are orthogonal. And there is still root minus 1 P minus Q. Is positive on VPQ. This is so polarization. So this so this is a polarized complex variation of structure. So and so in this case, so the direct sum this is a positive definite, so it gives Hermitian metric. So this gives pure harmonic metric. Sorry, so if this is pure harmonic metric, then this is called polarized complex variation of structures. Sorry. So these are basic examples. And then, so let me explain. So wide harmonic bundles. So let me remind you the definition of wide harmonic bundles. So suppose so we are given a hypersurface. So for simplicity, we assume this is normal crossing. And suppose let E del E bar theta H be harmonic bundle on X minus D I plus H. Then, as I mentioned, we have the spectral. So this induces the Higgs bundle induces a coherent shift on the cotangent bundle of X, X minus H, and theta sigma denotes the support of this coherent shift, support of this one, support. And this is called spectral variety of the harmonic bundle. And then so we say harmonic bundle is called wild if the closure of the spectral variety in t star x so this is not important, but log h tensor O and h. So if we consider the closure of the spectral variety in the logarithmic cotangent band set by O and h is proper over x. And so this is not precise. So n is just take so we can take n just locally around each point of h. So n is just given by local. Anyway, so very briefly, spectral variety is meromorphic on x. Then this harmonic band is called wild. And sometimes it is convenient to consider a subclass of wide harmonic bundle called tame. So let me mention it. So this harmonic bundle is called tame if the spectral variety, the closure of the spectral variety in the logarithmic cotangent bundle is proper over x. Okay, so let me show you an easy example of wide harmonic bundles. So if I use this notation as sheaf of meromorphic functions on x, and pole of x is contained in H. So if we take some meromorphic, sorry, I'm sorry, here. So if we take, if we consider holomorphic line bundle on x minus h, and if we take meromorphic function on x whose pole is contained in h, and so if we consider the Higgs field, which is obtained as a derivative of f, and consider the symmetric, then then this is wide harmonic bundles. Because spectral, in this case, spectral variety is just image of theta. And so if we take large n at this locally, then this is proper over x. The closure of this guy is proper over x. So this is wide harmonic bundle.
What the definition of this sheaf was, of which sigma theta was the support?
Sorry. Here, this one?
Yes.
So Higgs bundle implies, gives E is naturally symmetric product of x minus h. So this is tangent sheaf, and this is modulo over the symmetric product of the tangent sheaf. So this gives coherent sheaf on the cotangent bundle of x minus h. and and if we are given polarized variation, polarized complex variation of Hoshi structure on x minus h, then this is tame. Because in this case, Higgs field is given as so if nabla satisfies this condition, then we have the decomposition of nabla equal theta dagger plus nabla u plus theta. I mean, so theta dagger map this one is so nabla theta dagger expresses the component of nabla which maps this one to this part, and this part expresses the part of nabla which maps VPQ to this part, and theta expresses this part. So in particular, so if we take the composition this one to del plus del bar, then V del bar, so this is H, theta H is harmonic boundary. And in this case, theta is nilpotent because the map so it gives a shifting of degrees. So theta is nilpotent. Which means the spectral variety is just a zero section. So if polarized variation structure is given on x minus h, then it is always tame. Okay, so then so let me explain basic examples in the one-dimensional case of wide harmonic boundary. Over functional disk. So let y denotes disk, and we have the origin of the disk, and if we take meromorphic function y whose pole is contained in 0, then as I mentioned, we have the wide harmonic bundle given by O y minus 0 and dA Higgs field, which is the derivative of A, and the metric H. This is again trivial one. H. So we have this kind of wide harmonic bundles, and so if we take pull back, if we take the map from y to y given by phi z equal the m square. Then we can take the push forward of this harmonic boundary by phi. I mean, just so we have the push forward. So this is sorry, or y minus sorry 0. So this is covering map on y minus 0. So we have the push forward of vector boundary in a very most naive sense, and we have the naturally induced Higgs field and the metric on the push forward. So, and it gives wide harmonic boundary on y equals 0. So we have this type of wide harmonic boundary on y equals 0 or y 0. And for if we take pair of real numbers and complex numbers, then we have harmonic boundary given by O y minus 0. So I take yes, O y minus 0, and Higgs field is given by alpha d0 over z, and the metric h11 equal z minus 2 square, 2a square. Then again, this is easy to check. Gives harmonic boundaries, and in this case, this is actually term harmonic boundaries. In this case, the log of z minus 2 square is harmonic function, so it's easy to check. The curvature of this connection is trivial. And so we have this example, and we also have so if we take sorry?
What is the monodromy of the corresponding flat bundle?
In this case, maybe I will explain it later, but in this case, so let me say, so so in this case, minus sorry, formula is given by alpha lambda inverse alpha minus a minus lambda alpha bar, and lambda equal in the case alpha minus a minus alpha bar. So the monodromy is exponential maybe minus 3 pi to 2 pi root minus 1 alpha minus a minus alpha bar. This is the monodromy corresponding. So I'm not sure this signature, but okay. And so if we take nilpotent map nilpotent matrix. We have so this is not uniquely determined for n, but so we can we have Taylor harmonic bundle underlying variation, polarized variation Hodge structures. Whose with monodromy exponential of 2 pi root minus 1 n. So this is not canonically defined for n, but we have some Taylor harmonic bundle or for the variation Hodge structure whose monodromy is conjugate to this one. So this is also basic examples. Then, so by taking direct sum of the tensor product and direct sum, we may have this type of harmonic bundles, and this is again wide harmonic. So this is again wide harmonic bundles. So this is again typical example of harmonic bundles, and so I mentioned the local theory of wide harmonic bundles in my previous talk, and we can say the goal of the local theory of wide harmonic bundle is to show general wide harmonic bundle is very close to this type of wide harmonic bundles. So this is a very typical example, and sorry, important to understand. And so how to show general one is close to such special one. So I'd like to explain it in the 10 case today. So today we consider 10 case. And this is essentially appeared in the work of Simpson. So we consider general or Taylor harmonic bundle on Taylor harmonic bundle on Y0. Then we have the decomposition precisely we have to shrink y around 0. Maybe I will forget to, maybe sometimes I will forget to mention this kind of shrinking of y. So because we are interested in the behavior around 0, so it's not so important problem. But maybe anyway, so after shrinking y, we have the decomposition like this. Such that decomposition of the Higgs bundle such that spectral variety the closure of this one and closure in logarithmic cotangent bundle of y and the intersection of this one and the fiber over 1 fiber so that p star y of 0 over 0. So this fiber is naturally isomorphic to C, and this intersection is alpha. So if we shrink y, then we have the decomposition of Higgs field such that the spectral variety of the closure of the spectral variety of theta alpha intersects with the fiber over 0 at alpha. So in this way, first we have some sets of alpha complex numbers such that E alpha is non-zero. And we also consider the following things. So for any real number, so E is just given on y minus 0. So we like to extend across 0. So for any real number, let PAE U denotes the space of and if we U is an open subset of y which contains 0, then PAEU denotes the space of holomorphic sections of E over U minus 0 such that its norm with respect to H is dominated in this way. Sorry, maybe it's better to write gamma So in this way, we obtain OY module PAE whose restriction to y minus 0 is equal to the original holomorphic vector bundle E. And so P star E is sub of PAE for any R, and PE is union of PAE. We consider this kind of O1 module Sorry, could you repeat? Sorry.
I think you wrote P star, P lower star E.
This means just the tuple of PAE.
Huge tuple of lots of those.
Just P star E means just so we'd like to consider this kind all of PAE. I mean, not specific PAE. I mean,
I see.
yeah, so maybe it's not so good notation.
I think people at this with the filtration of the Stokes level.
And then proportion. This is proved by Simpson. So in this case, PAE, each PAE is locally or locally free modules. I mean, they are coherent. And so so let me mention a brief outline of how we obtain this kind of claim. So in this case, so by the equation of the condition for harmonic bundles, the curvature of this vector bundle E with metric is equal to minus the commutator of theta, and it's a joint. And Simpson proved this is dominated by this kind of dz bar.
What was theta now?
Sorry?
What was theta? I mean, E was one of these harmonic ones. What was E in this?
Sorry. E is this vector bundle. So we are given tame harmonic bundle on y0.
Any tame harmonic bundle.
Yeah, any tame harmonic bundle. Yeah. So this is a general claim for any tame harmonic bundles. So this means the curvature of the harmonic vector bundle with the Hamilton metric is bounded with respect to the Poincare metric, and such bundle is called acceptable bundles. And Professor Griffiths and Professor Conrad developed some general theory about this type of bundles. Then we can, so applying their theory in the one-dimensional case, we obtain this sheaf is coherent. So in this case, we obtain locally free modules. So in the high-dimensional case, so let me comment into the high-dimensional case. So in the high-dimensional case, it's not enough to show coherent. So we have to prove something more. But anyway, even in the high-dimensional case, we can obtain this kind of locally freeness property. But anyway, so
You can obtain some sort of similar
sorry.
Did you say you can obtain some similarly locally free modules?
Yeah. Even in the high-dimensional case, we can obtain similar claims. Yeah. I mean, not only coherent, but also locally free property in the high-dimensional case. Then and moreover,
Sorry, I am confused about what it says. And first, I cannot read the exponent. Could you tell me what it is? So the big O of there is Z and a log, but what is the exponent?
sorry. This is this is called the section of NE tensor omega 11. So this is expressed as f equal f times dz bar, and f is dominated by z minus 2 square log z minus 2 square. So maybe it's better to write this one here.
Is it the definition of acceptable, or is it
Yeah.
the bundle is acceptable? Or
Yeah, so if curvature is dominated by curvature is bounded with respect to the Poincare metric, then such a holomorphic vector bundle with Hermitian metric is called acceptable. Yeah. And general theory was developed. General theory for acceptable bundle was studied by Kohlner and Griffiths, and in the one-dimensional case, by applying their theory, we can obtain the coherentness of this one, and it implies locally free property in the one-dimensional case. And in the high-dimensional case, to prove locally freeness, we have to refine their theory, but in the one-dimensional case, it's enough to. And moreover, we obtain theta PAE is contained in PATE tensor omega 1 log 0. This is also again Simpson. So we need some estimate for theta, which is given by Simpson. Then we set group PE, group APE as PAE divided by PBE. So this is a sheaf supported at the origin, but we regard this one as just a sheaf vector space. And we have the action of residue of theta here. Then we have the generalized eigen decomposition of this space. Like this one. And the nilpotent part of the residue on this part is denoted by N0 A alpha. On group PE. And so the alpha here is the same as alpha here. Sorry.
is it then you are telling one method decomposition, but how is it good with respect to H?
Yes. So I write alpha is contained similar to almost all. We have just a finite set and finite subset, and this finite set appears in here.
But is this the composition almost orthogonal?
Yeah, so we have some estimate with respect to so in this case so if we take section of E alpha, U beta of E beta and alpha beta, then the metric this product is dominated by the epsilon we have this type of estimate, and so if we don't have this one, it is just ordinary Schwarz lemma, and but we have this one, and so if this is small, this part is very small, and so in this sense we have asymptotic orthogonal. So anyway, so we have so this type of pair and nilpotent maps. So we'd like to say so E del E bar theta H is close to alpha tensor V N0 A alpha. And for that purpose, sorry, it is something, we have to study something more. So, so for any complex number lambda, we have the whole vector bundle and with lambda connection. And if lambda equals 0, this is the original Higgs bundle. And in this case, again, we consider the sheaf given in this way. So we obtain P or OI module P A E lambda, and and again this is locally free, because in this case the curvature is of this boundary is given by -1 plus lambda square theta theta, and so it is easy by the same reason we can show this is locally free. And we also have d lambda is logarithmic, tensor so we have the actions of group P B E lambda, and you have the general eigendecompositions of this space. And we would, again we obtain nilpotent part of this duon here. Then proposition. This is again essentially Simpson. So we have the map k lambda. We define k lambda from r times c times r times c, given as k lambda a alpha as a plus 2 real part of lambda alpha bar and alpha minus a lambda minus alpha bar lambda square. Then we can show dimension of group P A alpha E0 equal to dimension of group P K lambda A alpha E lambda is equal. And moreover, N0 A alpha and N lambda K lambda A alpha are conjugate. So nilpotent parts are essentially the same. So sorry, so I have to finish. So sorry, so yeah. So we consider group P E lambda A alpha E lambda. So by considering all lambda, this gives harmonic vector bundle on C lambda, and N0 A K lambda A alpha gives nilpotent endomorphism on here. And the conjugacy class is the same, so we have the weight filtration of this endomorphism given by vector subbundles. And so we obtain this kind of object from tame harmonic bundles, but this is just given C lambda, but we may consider theta dagger H. This is tame harmonic bundle. X, y dagger on y dagger 0. And from this, by applying the same construction, P K mu minus A alpha bar E dagger mu on C mu, and N dagger mu K mu minus A alpha bar gives nilpotent endomorphism, and we have the weight filtration, which is filtration by subbundles. And in this case, so I don't explain details, but we can group this guy and this guy by lambda equal mu inverse. I mean, for lambda equal mu inverse, sorry?
Which
flavor. He studied what he wrote is the case lambda equals 0 and 1. So he does not write this construction, but in his preprint about mixed twistor structures, he suggests this construction, and he conjectured. So we can group these two vector bundles by. So we have natural isomorphism of k lambda a alpha e, so e lambda, and group p e k mu minus a alpha bar e daga mu for lambda equal mu inverse, and lambda inverse n lambda a alpha equal minus mu inverse n mu minus a alpha bar. We have canonical isomorphism in this one, and not canonical depending on the tangent vector at 0, but we have the isomorphism, and under the isomorphism we have this identification. So by gluing, we obtain some vector bundles on P1, and morphism from here to here. We obtain this kind of objects, and from the metric, we obtain pairing of VA alpha and sigma star VA alpha. Sigma is the involution, anti-holomorphic involution of P1 given by sigma lambda equal minus lambda bar inverse. And we can show this data gives gives polarized mixed weight filtration twistor structure. And as in the Hodge case, we have the corresponding twistor nilpotent orbit Na alpha. So which write V Na alpha. Then we can show theta h is close to -1, 0, L A alpha tensor V Na alpha. So this claim is rather ambiguous, but roughly the given Taylor boundary is very close to this type of special Taylor harmonic bundles. So in this way we can understand the structure of Taylor harmonic bundles, local property of Taylor harmonic bundles. So I'll stop here.